Please let me what you think about this. This is an example when we're calculating a force acting from a large object on a small object. The large object is the Earth, and the small object is 1 kilogram weight placed on its surface. These two vertical bars are supposed to be here to represent the magnitude of the force. I'm not sure why it's shifted, but it doesn't really matter. So the magnitude of the force of gravity is equal to the product of, well, technically 4 numbers. Yeah. Product. This is also is a product in a way. And 1 kilogram weight is placed on the surface. What do you think should be the magnitude of the force acting from the Earth on this weight to be equal to? And let's see. I'll be back. I am back. Well, we've got a distribution, and well, there are different ways to calculate that force. For example, we can apply the Newton's law, or it's a 1 kilogram weight here on the surface. We know it's supposed to be equal to mg. So this question is not about calculating the weight. This question about calculating g. We've measured it before, but now, with the application of the Newton's law for gravitational attraction, we can calculate the value of g. This is what it is. There is a force of gravity acting on its. And on one hand, it's supposed to be equal to this. On another hand, this is what g is supposed to be equal to. This is just a definition of free fall acceleration. And if we plug numbers in, we get 9.8 or about 10. However, now we can make a step ahead. For example, we can ask, what if we are not on the surface? What if we move away? What if we're much higher? Well, the only difference now is that when we are applying the Newton's law of gravitation, we have to calculate, well, let's say G, using the same equation. It doesn't have to be Earth. It works for any planet. But now we just need to add the altitude, the height above the surface. And wherever it is, that's going to be the number. So we should change calculation. We still keep the same constant. We, of course, keep the same mass. But the distance is supposed to be different wherever it is. That's it. Just have to keep in mind how the law is supposed to be applied. When we're applying the law, we always have to use this distance. What's happening today? Everything is thick. That's sick. All right. Please draw a Freebody diagram for this situation. And when we read the text of a problem, we try to imagine what is happening. Here we have three objects. There is the Earth, there is the Moon, okay. We know the distance. It's an average distance, of course, because it changes slightly, but still, and that distance is 300 megameters. And right here in the middle we have another object. Now, naturally, we want to start drawing forces. For example, there is a force acting from the Moon and the Earth. And they attract each other. But now it's a moment when we need to control our thoughts. The Freebody diagram has to be drawn for the satellite. That's the object for which we have given information. So we just don't need to draw any forces acting on anything else. And people do that and get confused. So there's only one object for which we need to draw a Freebody diagram, right? And of course, there is a force of gravity due to Earth. And there is another force of gravity due to the Moon, which is stronger. Earth, we know that the distance from the Earth to the satellite is a half of d and same. So distance is the same, but the Earth is heavier, so it should exert stronger force. What do we do now? Now we just calculate wherever it is. So again, diagram. It has no memory today, which is naturally for Monday. So the magnitude of the force acting from the Earth. One ton, it's 1,000 kilograms. And the mass of the Earth, 6.4. We just... what happened here? $385. You can finish the calculation. Same satellite, same distance. This part is about using your calculator. The mass of the moon, 7. That's going to be newtons. And of course, if we check the numbers, this number will be stronger, larger than that number. There's a natural question we can ask. All right, let's say this satellite travels from the moon back to Earth. So in that case, when it's getting closer and closer to the Earth, the force acting from the Earth will be stronger, the force acting from the moon will be weaker, and well, eventually it crashes and everybody dies. So that's a bad scenario. The good scenario, it starts from here and travels toward the moon. In that case, the force acting from the moon getting stronger and stronger, the force acting from the Earth getting weaker and weaker, and eventually there has to be a place where these two forces become equal to each other. You can ask, where is that place? I can say, here. See it? Well, but if we want to describe that place, of course, we need to calculate, for example, this distance. And this is where we have to do some simple geometry. If distance between, let's say, moon and the satellite is x meters, the distance between the Earth and the satellite will be equal to what? D minus x. And the forces at this location only must have exactly same magnitude. So how do we write it? Well, the force acting from the Earth on the satellite divided by distance squared must be equal to the force acting from the moon on a satellite divided by the distance squared. That's it. And now you have a choice. And if you have it done already, you could have solved it as a quadratic equation. And we know how to do that. Just apply quadratic formula. But in this particular situation, we have a shortcut. First of all, if we look at the unknown, what makes this equation hard. Two things. First, the unknown x is in the denominator on both sides. So what's the easiest way to get rid of the denominator? Flip it. So you first you can cancel some stuff. But if you flip it, your equation now is simpler. This is the mass of the Earth, and this is the mass of the Moon. Still a little bit more complicated than we want to. But we ask a question, what does make it complicated? Now everything is squared. But again, in this situation, it's squared on both sides. What's the easiest way to get rid of a square? Take a square root. We say it unsquare, right? So we can unsquare, and you get an equation which now can be solved like 10 times faster than if you would be doing quadratic equations. You can do cross multiply, square parentheses, rearrange the variables. Nothing wrong with that except one thing, it takes much longer time. Well, circular orbits. Again, we know everything about it because it's just a combination of everything we've learned about circular motion, Newton's laws. Let's say the same satellite is orbiting the Earth on its way back or before it starts flying away. So what can we calculate? What can we find? Now we can find everything. So diagram. There is a force of gravity acting on the satellite. The equation for the force of gravity is exactly the same as before. Just in general, we gotta use the total distance from the center of the Earth to the satellite, which is equal to the radius of the Earth, average radius plus the altitude. And the equation, which relates acceleration, does it have acceleration? How does it point? Because it's a circular motion, and for the circular motion, the acceleration is never zero. And for the motion with constant speed, the acceleration has a name, centripetal acceleration. It points always toward the center, nothing new. We just have to write down that mass of the satellite times centripetal acceleration should be equal to the force, which is this. And again, as we've seen it before many times, the mass of the satellite doesn't matter because it's getting canceled. And centripetal acceleration equals speed squared divided by the radius of the circle, not the radius of the Earth. And now we have r on the left, r squared on the right, so we can cancel one r and solve it for the speed. This is a standard expression for orbital speed, not just for the Earth. Little m doesn't matter. Big M represents the mass of so-called central object or central body. And about that central body, there is a satellite orbiting with orbital speed. At this point, we can just plug the numbers in and calculate. 6.7, negative 11, 6 times 24, 6.46. There is a slide later which says if the altitude is very low, this number should be about 8 kilometers per second. So if altitude increases, So the speed decreases, maybe 7 point something, etc., etc. But now, what else can we calculate? A period, that's a circular motion. If we know the speed, the period is equal to, well, the speed is equal to distance traveled, which is 2 pi r over the period. So the period equals 2 pi r over the speed. Or people write it like 2 pi r divided by the speed. So we have to keep the square root, but r gm. And of course, we don't like square roots. So people square it. And if you square both sides, turns out the period squared will be proportional to radius cubed. This relationship has been derived from measurements by Kepler. That's the third Kepler's law. And there's a slide with this. So he spent years analyzing data on planetary motion. And he found, and it was more complicated because actual planets don't travel in circles. But if we apply this simple theory, Kepler's law, just there. What else can we calculate? Well, of course, energy. For example, kinetic energy has to be equal to mv squared over r, which depends on the mass, of course. Kinetic energy depends on the mass of the object. But we can rewrite it in terms of central mass. 2. Getting ahead of myself. Potential energy will be soon also calculated. mv squared over 2. m over 2 and v squared. What is it equal to? V squared equals gm over r. That's it, gm over r. gm over r. So how would we rewrite it? 1/2 g little m big M over r. That's how we can calculate kinetic energy. But much more interesting fact is the potential energy for this system. Two objects attracting each other. The potential energy is equal to, the exact expression for the potential energy is this. Now, if anyone remembers the math self-test we've done, that was a question like 35 or something like that. You were told to calculate two expressions divided by each other. One like this, second like that. Now we can do it, understanding what we're doing. For example, we can calculate the ratio between a kinetic energy of a satellite and its potential energy. What should we calculate? 1/2 divided by it works for any satellite orbiting any central mass. So these variables could be any. But what is happening to all those variables? G and G, little m, big M, little r, they disappear, they get canceled. So what's left? A minus and a half. This is one of the neatest, most beautiful results. For any satellite in the universe, if you calculate this ratio, it's going to be exactly the same number. Again and again and again and again. Kind of cool. It might look strange. Kinetic energy is negative. No, it's not. Potential energy is negative. If you're multiplying two negative numbers, you get the positive result. And of course, we can calculate total energy if we want to, because total energy, E total, is just kinetic plus potential. We can do it differently, but in this situation, kinetic equals this, potential equals that. Turns out that we also have a universal ratio, total energy over potential energy is equal to 1/2. And since potential energy is negative, total energy is negative, what does it mean? It means if we want to break it apart, we have to do positive work on it. That's a bound system. That's a standard signature sign of the system which is bound. It's holds itself. If we want to break it, we have to do something. Like the satellite should start an engine, and that engine would do work, and eventually that work would bring the satellite farther and farther away, and it could fly away. And how much work should it be done? Well, work kinetic energy theorem can say that. All right. Any questions? Yes.
I just want to clarify that it's kinetic energy over potential energy?
Yep.
Like energy total over potential energy?
Yeah. Exactly like in the math tests done before. So this is the Kepler's third law, and this is a calculation for the so-called first orbital speed. If a satellite starts traveling faster and faster and faster, first of all, the orbit becomes not circular anymore, elliptical, and then eventually becomes parabolic, hyperbolic, and it flies away. One more example. Let's say two objects traveling. Nothing different. We just have to apply the same kind of reasoning twice. And here we have to be careful with distances, because this should be R1. And this should be R2. So again, I prefer every time starting from the scratch, for writing an equation, Newton's second law. Well, mass canceled. And V1 will be equal to, again, square root of the same expression we had before. But now we don't have to solve it twice. We can immediately write the expression for V2. We just replace number is subscript 1, with subscript 2. Right? Right. Now we just look at the picture. The first speed should be equal to this, divided by 2 radii. The second speed should be equal to this. And what number should I write for the coefficient? How many big R's? 8. 7 is the altitude, plus 1 because of the radius. It looks like we have too many unknowns, but when we are looking for the ratio, they get canceled. So for example, here we get this divided by this. The central mass, big M, is not given. The radius of the planet, R, is not given. But they don't matter. I forgot to. they're getting canceled. So please tell me the result. This is a fraction of two fractions, which also has a square root in the numerator and denominator. So what's the result?
0.065.
Anybody else?
For
So I'm not sure how would be the most convenient way to do it. It depends. Different people would have done it differently. So for example, one step would have been doing this. If you divide by a fraction, it's the same as to multiply by the inverse fraction. So this is this problem is more about mathematics than about physics. Well, so we've seen this slide, and this is just to illustrate how to calculate that minimum speed the satellite should have in order to fly away from central mass. It starts from a certain orbit, and it travels at that speed, but eventually, if it moves away, what's happening? It slows down, which means kinetic energy getting smaller and smaller, and we assume that eventually very far away kinetic energy is zero, and so does potential energy, because when potential energy, when we use expression for potential energy, when the distance are getting infinitely large, greater and greater and greater and greater and greater, this number becomes infinitely small, which is zero. And if we apply the law of conservation of energy, straightforwardly just solve it. For the satellite which wants to escape the Earth, the speed should be about 11 kilometers per second. So we don't really know how fast should you travel to escape New York or Los Angeles. But if you want to escape the Earth, that's about 11 kilometers per second. Any questions, please? Please. All right. In that case, moving on. Yes? If it's about force, in that particular situation, force of gravity, we start from the Newton's second law, and we use the fact that for the motion, uniform circular motion, motion with constant speed, acceleration always points toward the center of the orbit and equals v squared over r. And we use the fact that for any two objects, force of gravity acting between those objects is equal to, again, according to the Newton's fourth law, Newton's law of gravity, So this is what has been done here. Here, the Newton's law, then acceleration, and then we do some algebra, and here I just did it again. Where is it? All right, so temperature. Well, we know a lot of it from our everyday life experience. We can feel it, unfortunately. If we try to feel the temperature, we can't say very accurately the number which it represents, but we have plenty of devices we can use to measure temperature. For example, this one. Or a digital thermometer. There are many types of. You will be using something like this if you're going to do the last lab. So it has a screen, it's just a smaller version of this. Here you can read temperature. Here, well, this device measures the temperature at the tip, at the end of, well, basically it's two different metals sorted together. It's a so-called thermocouple. If temperature changes, it changes the voltage. It basically measures voltage. It has, inside it, has a conversion factor between temperature and volts. That's it. And historically, we have several. This is actually cool. You can point at anything and read the temperature right here. Of course, you cannot because you can see it, but I see 68 Fahrenheit, for example, the temperature of this table. Where do you get it? Home Depot. Well, historically, all we need to do to establish, you can establish your own scale if you want to, but that's what has been done by Dr. Celsius, not Dr. Seuss. Celsius. He used iced water. You place something in iced water and wait long enough. Long enough. Okay, let's try. You should see how the needle moves. And when you, well, we can do it with this guy. When you wait long enough, it eventually stops moving. When temperature doesn't change anymore, we say thermal equilibrium is reached. And Dr. Celsius said, I call it zero. Because he was first, he could do that. And then he boiled some water, placed something like this in water. Does it move? Yeah, it moved. So eventually, the needle stops moving. So he drew a line and he says, I call it 100. And that's how he invented his temperature scale. And of course, he divided that region in 100 equals portions and call every portion my degrees, well, degrees of Celsius, not his degrees. And that's what most of the people use in the world. There's one country which doesn't use Celsius. But we don't care because we always have a conversion factor. Professor Fahrenheit used different way to set initial and final temperatures. There is also the third temperature scale, which we call absolute temperature scale, or Kelvin, which physicists use. And the conversion factor between temperature measured in Celsius and temperature measured in Kelvin is just a fixed number, which is good because very often we don't really need to know temperature. We only need to know the change in it, how much change happened. And the change in Celsius is equal to the change in Kelvin. It is not equal in Fahrenheit. That's why we don't use Fahrenheit for calculations, just for weather report. Now, how does temperature affect things? Well, the idea is very simple. That's what everybody have noticed. If we have an object and we warm it up, normally it expands, normally. There's some exceptions. But if you have a rod, you pour some gasoline or kerosene, light it up, so it's getting warmer and warmer. And you can see when it starts pushing, so there is some, let's see, if it starts pushing, we can see, we can measure actually how much longer it becomes. I don't have a gasoline. Does it move? It does. I see it. All metals expand. And of course, we can measure how much longer it becomes for all materials and relate the change in the length with the change in the temperature and the coefficient which relates those variables. Alpha has a name, the coefficient of linear expansion. And you see, this equation has a delta T in it. So if you Google, some numbers might give you 1 over Celsius, some numbers might give you, some sources, 1 over Kelvin. But we know it will not matter, so don't be confused by that. Of course, for natural materials, it's a very small number. We have to heat it up really, really hard to make it visibly longer. If we take two different metals glued up together, what should happen if we warm it up? They both should get longer, but differently, because they have different coefficient. In that case, what do we see is the amount of bending depends on the temperature increase, and that's how first thermostat used to work. If it's getting hotter and hotter, it bends more and more, and you can attach it to a scale and read the temperature. Question? I've got a ring and a ball. And the ring is too small for the ball to get through. See? This is a balancing exercise. Anyway, I'm just giving you time. I'm going to heat it up, the ring. And the question is, what do you expect to happen? I wouldn't use this to measure temperature, but I could use a thermocouple. It shrinks. No, it expands. See? Of course, it's if you look at what's happening to the circumference, it's the same linear expansion. And if I had not a ring, but let's say a square, the area would increase And of course, if we have a bulky material, a piece of metal cube of copper, for example, it would expand in all 3 dimensions. So if you want to calculate how much more volume it expands, we could use exactly the same equation. For each side, we can use the coefficient of linear expansion, just cube. And turns out that the coefficient of volumetric expansion is just equal to 3 times coefficient of linear expansion. Heat. Heat is energy. Special type of energy. When we have a hot object and a cold object put together and wait, what should happen? The hot object, we know, becomes colder. The cold becomes warmer. There is some energy exchange. It's not due to Newton's law. No. It's due to a different law. We're going to talk about it in the future. It's not related to mechanics at all. It's just a fact. If you have 2 objects, one is cold, one is hot, put together, hot becomes colder, cold becomes hotter. So there is some energy flow. This is what happens when we put them in contact. Another way is to use a radiation. For example, we have a heater. Yeah. It doesn't touch you, but it emits infrared light, which warms everything up. And the amount of energy, of course, depends on many circumstances. So this is a thought experiment. You should use your imagination. Let's say you have a freezer, you open it. You take a piece of ice out of a freezer. You, of course, don't put it on a heat plate directly. You have some kind of a cup, put it in a cup, put a lid on it. Then you put it on a heat plate, turn it on. You place a thermocouple so you can measure temperature. It has a little window. You can see what's happening inside. So you have to read the question carefully. And choose your answers carefully. A standard freezer provides temperature about 95 Celsius, something like that. You can always convert into Fahrenheit if you want to. But what's important, it's below the freezing temperature. Freezing temperature in Celsius is 0. So, if you have done this experiment, you should know that it doesn't immediately start melting. No. The melting starts at the melting temperature. That's why we call it melting temperature, because melting starts at it. Not below, not above, at the melting temperature. So at first, this substance, ice in our example, needs, well, some time to reach that temperature. So at first, it will be warming up to 0 Celsius. It takes some time. The time depends on the amount of ice. And now it starts melting. When it starts melting, if you measure temperature, the temperature doesn't change. Right here, so if you had before just a piece of solid ice, right here you start having a mixture, ice and water. And until ice completely melts, temperature doesn't change at all. After that, we have water, only water left. And of course, if we keep heating it up, it keeps warming up. Until what? Until 212 Fahrenheit or 100 of Celsius. When it reaches 100 of Celsius, what starts happening? Boils. It's a liquid to gas transition. Yeah. That gas has a special name, vapor, but still. Here, we will have a mixture of a liquid and gas. Of course, if we keep holding this container on a heat plate, eventually there is no water left. But if we keep warming up, now gas, vapor will be heating up. And, well, if we keep, eventually it might go to plasma if we're really, really powerful. Yeah, but it's outside of the scope of this graph. That's what's happening. So we can only have two options: warming up, or the general name for this situation is a phase transition. There've been solid phase, and now it's a liquid phase. Liquid phase, and now it's a gaseous phase transition. When phase transition is happening, temperature doesn't change. When temperature changes, there is no phase change. That's it. And of course, we could do it. So this statement is wrong. It's not immediately. Of course, we can do it backwards. Let's say we start from gas, vapor, and put it in a freezer and wait and wait. So at first it cools down, reaches 100 degrees. The phase transition always happening at the same temperature. Well, it depends on pressure, but under regular pressure it's 100 Celsius, 212 Fahrenheit. So it starts condensing. Condensation eventually leads to just water. Water cools down, water freezes. Eventually we get ice. Ice might keep cooling down. And of course, if we have to achieve large temperature change, we have to spend a lot of energy. Or if we need to melt a lot of ice, we have to spend a lot of energy. So the amount of energy depends on what? Well, on temperature change, or on mass, and internal properties. Some molecules are bigger, some smaller, some closer, some farther. How do we describe internal properties? We use some measurable variables. This variable has a name: latent heat of fusion, latent heat of evaporation, latent heat in general. And this tells how much energy we need to spend to, let's say, melt 1 kilogram of something. If m equals 1, that's the amount of energy what it is. We measure it. You can now Google latent heat of water. A number pops up, about 4,000 joules. That's C. Latent heat of water, about 300,000 joules per kilogram. Now, if we go to warming up or cooling down, the amount of heat is proportional to temperature change. This coefficient tells us how much heat do we need to spend to warm it up by 1 degree if difference is 1. Of course, it's been measured. But also this coefficient depends on the mass. If we have a small piece of ice, we need a certain amount of energy to warm it up by 1 degree. A huge piece of ice requires more energy to warm it up by 1 degree. So we make one next step. We calculate this ratio. This has a name, heat capacity. This has a name, specific heat capacity, but people call it specific heat. That's it. Specific heat related to the substance, specific heat of ice, specific heat of water, specific heat of copper. This is related to an object, heat capacity of 2 kilograms of ice. And now we can write these equations for each part of this graph. Warming up, phase transition, temperature change, phase transition, temperature change, or backwards. Temperature change, phase transition, temperature change, phase transition, temperature change. The difference between these type of equations. When a system absorbs energy, the amount of energy it absorbs, Q, is positive. When a system releases energy to surroundings, Q is negative. And this equation takes care of it automatically. When temperature increases, this is a positive difference. Q is positive. When temperature decreases, we have to use a small number and subtract large initial number. This difference is negative. Q is automatically negative. Here we must remember. When should we write a plus? When should we write a minus? These equations represent the magnitude of the heat. When the system, an object, absorbs energy, it takes energy away from surroundings. The energy inside is more and more. In that case, Q should be positive. We have to choose a plus. When an object gives away the energy, it loses energy. We should choose a minus. We should do that. The equation doesn't take care about it automatically. We need to remember. That's it. Well, we said that. These are some examples for specific heat for different materials. Now, one more general statement. Let's say we put together several objects. Some are hot, some are cold. We know hot should start giving away energy, cold should start absorbing energy. Now, if we place that system into some kind of a container which insulates it from everything else, from the rest of the universe, in that case, the total energy of the system inside that container must remain constant, which means the total amount of energy some objects lost should be equal to the total amount of energy other objects absorbed. That's the law of conservation of energy. So how do we write it? We have two ways to write it down. The law of conservation of energy says there is no change in energy. Yeah? So a Q represents the change in energy, absorbing or releasing. So if we add all amount of energies for all objects, some should be positive, some should be negative, and the result, the sum should be equal to 0. Of course, we call it heat balance equation. But we also can rewrite it differently using magnitudes. If we add magnitudes for all heat absorbed by everything, and if we add magnitudes for all heat released by other objects, the amount should be equal to each other. That's a summary, all equations together. Now we're done with theory. Now we can start solving problems. And again, please, tell me what you think. a bullet travels oops. All right. A bullet travels. So it has a certain speed, it has a certain mass. It automatically means it has certain kinetic energy. When it hits the target, it stick to it. What is happening to that energy? Is kinetic energy conserved? No. It was not zero, now it is zero. Is mechanical energy conserved? No, if kinetic isn't. But energy in general must be conserved. That's its most important feature. So where does it go? Well, if we neglect any loss to like air or something else, all that energy should be transferred into the heat, internal heat of the bullet. You look confused. That's it. Well, there is some friction here. We neglect that. We only care about internal friction between the parts of the bullet inside it. Like in the experiment with the crashing can. Those parts were touching each other, moving relative to each other, so there is internal friction. And that's the only energy which is important. We neglect all other possible sources of the loss. That's the maximum, you know. So in this case, the law of conservation of energy should tell us this. Now we should choose. What equation should we use? Q equals mc delta T or Q equals Lm? Well, the answer depends on the process which should happen. And can it be melting? Probably not. 20 degrees of Celsius is too low. If it is not melting, it's supposed to be warming up. We cannot use both equations at the same time for the same process. So, warming up means this. This is this is the equation we can solve for the change in the temperature. Interestingly enough, m is cancelled. The question was about melting. And we know melting starts at a certain temperature, and we don't know if we have enough energy to reach that temperature. First, we have to solve this. There's a piece of information which is not given. The speed is given, right? The speed is 100. But we don't know specific heat of lead. So technically, we cannot answer this question unless we Google specific heat of lead. Now, normally you would find some weird unit on Google. You should pay attention. For example, here it says 22.4 kilojoules per kilogram. And 1 kilo has to be converted, and second has to be kept. If we use international system of units, we have to use joules and kilograms. So, oh, that's latent heat. Sorry. I'm distracted today. It's Monday. This is what I wanted. Sorry. That was latent heat. But what I said about this number is absolutely correct. That should be 22.4 times 10 to the third joules per kilogram. You just don't need to use it. And this is the number for the specific heat. And it's written in grams per Kelvin. So we keep joules. Can we keep Kelvin? That depends. If we're calculating delta T, change in Celsius and change in Kelvin the same. So we can, so it doesn't matter. We can actually write a Celsius or keep Kelvin. Doesn't matter. But we cannot use grams. A gram is 1/1000th of a kilogram. So the result is 128 joule per kilogram Kelvin. This is the number we need to use here. So we need to calculate this number. Depending on this number, we may have different scenario. So this is so I've got 39. What unit should we write? Since, again, this is the temperature change, we can use Celsius, we can use Kelvin. But since the initial temperature is given in Celsius, of course, we use Celsius. So the final temperature should be equal to the initial temperature plus the change. So 20 plus 39, 59 degrees of Celsius. The melting temperature is much, much higher. So it's not going to start melting. Yes?
How did you notice that kinetic energy?
Because energy, not mechanical energy, not kinetic energy, energy in general cannot disappear, cannot be created from anything. It only can be transferred. That's the law of conservation of energy in general. It's been mentioned before, and now we use it. Here we compare two different types of energy, mechanical energy and internal energy. But still it's energy. This is the law of conservation of mechanical energy. Theoretically, some energy goes away into heating air. Some energy goes away into heating the wall. Of course, we can imagine that all processes which happening in reality also require some energy. Some energy goes into sticking to the wall. But if we neglect all that stuff, the only energy left is energy which goes inside the bullet. And tomorrow we'll talk that this is actually also kinetic energy of the molecules moving inside the bullet. They just start moving faster. So it's not just some kind of fictional energy. No. If we look inside, those molecules just now move faster than before. All right, if we talk about yes?
How do we decide which equation for Q to use again?
It depends on the process. This is what we should keep in mind. This is only what can happen. Warming up or cooling down. And for that's what we call temperature change. And for that we use Q equals Cm delta T. phase transition only happens at specific certain temperatures, which called phase transition temperature. So if the object is above or below a phase transition temperature, it can't change its phase. It cannot melt, it cannot. So in this situation, I kind of know that the lead melts at 300, where 300, what's the number? 27.5 degrees of Celsius. So if we start from 20 degrees, I assumed, and then I checked it, that the final temperature still will be lower, which means that cannot be phase transition, which means that can only be temperature change. And for the temperature change, this is the equation we need to use. When something is happening, we always ask the same question: what happened here and now, phase transition or temperature change? That cannot be both, that's one or another. And for the phase transition, the system must be at the phase transition temperature. Yes?
The latent heat that you gave us was 128 joules per kilogram.
That's not the latent heat. 128 is specific heat. Latent heat is 22.4 times 10 to the third. This number we would have used if the bullet would reach the temperature of 327.5 and still some energy would be left, so it would start melting.
My question would be, let's see where kilogram.
If you solve for temperature change, you should write Q over Cm. In units is joules over, so a joule over kilogram Kelvin times kilogram. So joules and joules getting cancelled, kilograms and kilograms getting cancelled, and 1 over K is K.
Other side of the equation.
Mm, which equation do you mean? This or that? There are two equations. I didn't use that equation. I used this equation. If we use this equation, these are units. If we use that equation, the unit for latent heat is a joule over a kilogram. That's it. It has no temperature. So nothing else to say here. Latent heat is energy over mass, joule over kilogram. You had a question. Okay. Did I answer your question? All right. In that case, you should ask a better question. Better means clearer. Yes?
Delta T equals V squared over 2C.
In this situation, you have to if you work out those units, first you have to make a joule in some way, because C has a joule in it, and joule also has units. A joule is energy. It is a combination of what? Of a kilogram, of a meter squared, and a second squared. In that case, you got to go further. That's it. Do it at home. This is good exercise. This is meters per second squared. This is joule over kilogram Kelvin, but joule also is kilogram meter squared over second squared. So it will work out. Okay, water. Don't answer this question. So, all right. It means we still have 1 more minute. I don't have time to finish this, but you have time to answer the question now. Please answer this question. You need to make ice cubes for your party. Of course, you pour water in an ice tray, place it in the freezer, and the question is, what do you think is happening to the energy inside water? What does water do? Does it absorb energy or does it release energy? Should it gain some energy or should it lose some energy? Absorbing means gaining, taking away from the outside. Releasing means losing. Yes? You're lucky. All right. It's strange. Oh, yeah. So that's going to be first question tomorrow.